Okay, so we're going to learn about learning. So, but it's mostly going to be math. So, okay. So set S the Boolean functions. Okay, so let's say that we have a set S of Boolean functions, and we want to learn the function. This means that we have some algorithm that queries the function from S and tells us which function we have. So that's roughly what it means. So let's give a precise definition. Okay, so let's say that it can be epsilon lambda with R queries. Okay, so we check. So if there exists an algorithm let's say a randomized algorithm that checks the value of f on our inputs, and then it outputs a guess for what f is. And this which is a Boolean function, and we don't want necessarily G to be equal to f, but want it to be close to f with high probability. So we want the probability over G, so this randomized algorithm, and over x, that f of x is different than G of x. One that is smaller.
You don't insist that G belongs to us.
Yeah, that's how we don't.
And this is worst case over all functions in S?
Yes.
So G is random too, the output?
Yeah, so we take f and s, and given f, there is some randomized algorithm that outputs G. The probability, and f is equal to G with high probability. Okay. Yeah. Agrees with G on most inputs with high probability. So it turns out that one of the ways to get such algorithms is using Fourier analysis, and specifically using Fourier concentrations. So let's say that we have a function f on the Boolean cube. We can write f. We have a Fourier expansion of s, the sum of f at s chi s over all s subsets of n, where chi s is the product of I and s of xi, and these chi s are an orthonormal basis, and f at s is therefore the Fourier coefficients of f. And it turns out that some information about the Fourier coefficients of f, it can tell you that you can learn the function. Okay. Let's do this thing. Do I erase with this thing, or is it going to paint the wall?
You know how to use it. It should be water, yes.
They do it better than me, but
By the way, there was also a second part, so maybe next time you can. Okay, maybe it's good.
the second part is more important.
But hopefully you remember the definition of Fourier expansion, and learning is less important.
But there is more convention.
Okay. So we have this. Let's give another definition. What do I mean by Fourier concentration? So we say that F Fourier function let's say it's R epsilon Fourier concentrated. If there exists set F of size size R, such that the sum over all the full coefficients not in F but that's square, this is at most epsilon. So there exists R dominant Fourier coefficients that outside of this small set the Fourier mass is negligible. It turns out that if you have Fourier concentration, then you also have a learning algorithm.
One second now. So it's S is not an F, right?
Yes. Maybe it's too small. S. Yeah.
And who is R? Why R?
So
it's R epsilon Fourier concentrated.
Yeah.
If there exists a set F of Fourier coefficient of small size, of size R,
Size R.
such that all the mass is concentrated on this small set of Fourier coefficient. Okay, so maybe I can give an example. For example, you have the function fx equal to xi, then this is 1, 0 Fourier concentrated. And if you have you take any character, this is going to be 1, 0 Fourier concentrated because you just take f to be the character. And another example is that so if f depends only on j variables, so we call it a j junta. Yeah, so fx equal to xi is called the dictatorship, and this is called the j junta. And then it is 2 to the j is 0, also 0 Fourier concentrated. because they're only, it's supported of size 2 to the j, at most 2 to the j. Just, okay. That's an exercise, I guess. And the following theorem tells you that if you have full concentration, then you also have learning algorithms. And after that, I'll be able to stop talking about learning and only talk about full concentrations. So suppose that S is a set of Boolean functions. Such that every f in S is R epsilon Fourier concentrated, and then it epsilon over 2. Suppose that I have a set of functions that are fully concentrated, then I can learn this at S. So then there exists so I guess we call it S is epsilon learnable with then we have n r over epsilon to the O of 1 quads. So if R is a polynomial in n, then you have a polynomial time algorithm that learns the set S of Boolean functions. This is called the Godrech-Levin algorithm. And it's found applications in cryptography. So are there any questions so far? Because I don't write large enough or because I talk to Science. Okay.
Do you know what was Godrech-Levin's original application?
No. It wasn't a trick question, okay.
No.
Okay.
Because usually this R is pretty big, so it's not really polynomial time.
Right.
It's polynomial time in number of queries, maybe.
Yeah. But yeah, so there is like, if you know the Fourier-Entropy-Influence conjecture and learn DNFs, because we have total inference log n. Okay, never mind. So we'll talk about it later. Okay, but anyways, so we have this thing, and then we have the following meta problem that this leads us into, which is to find conditions that imply that f is R epsilon Fourier concentrated for a small r. So we know that if we have Fourier concentration, then we have learning. So we want to find conditions that imply that we do have Fourier concentration. Okay. Now we talk about a different topic, which is isoperimetric inequalities. It's going to turn out to be related. So suppose that I have a subset, the Boolean cube, the subset corresponds to a Boolean function. So the Boolean cube, you can view it as a graph where two vectors are connected by an edge if they differ in exactly one coordinate. And then you can talk about the edge boundary of a set. So the edge boundary of A is the number of okay, the set, let's say. Set of pair x and x with the j coordinate flipped, such that one of them is in the set and one of them is outside of the set. So the set of pairs of vectors that differ in exactly one coordinate, that one of them is in the set and the other one is not in the set. This is the edge boundary of the set.
And this sign means that you just flip one.
Yeah. Yeah, so switching back to additive notation. Okay, and then this is the notion of edge boundary, and then you can ask the isoperimetric problem. Okay, so suppose that you have some number A, and then you can ask what is the minimal edge boundary of the set A of size A.
Sorry, is it possible to move the bottom board up rather than down? Because now we cannot see.
Is it possible? Okay, so that's the isoperimetric problem, and this was solved a while ago. Now I forgot the, I think Harris. But not sure.
Harper. Harper.
Harper, okay. I was correct about the first derivative. And okay, and what year, if you're already? Okay. Okay. But we're not going to be interested in this problem that's already solved, but there is another problem that's still open, and that's the inverse isoperimetric problem. And then you can state it roughly like this. Suppose that
66.
66. Okay, so suppose that the edge boundary of A is close to the minimal possible value. Let's say up to a constant multiplicative factor, but it's interesting also if it's log n or more than that. What can we say about the structure of A? For small sets, we really don't know how to say anything about this inverse isoperimetric problem. But for large sets, we do know some stuff. So this is a really nice, interesting open problem to think about. Suppose that you have a small set A, and you know that the edge boundary is up to a constant, the minimal possible value. Can you say something about the set A? And there are some specific conjecture about how A should look like, and we don't know how to do this. So I can tell you about this if you're interested later. Okay. But one last definition is that the total influence of the indicator of a set A. So every Boolean function is the indicator of some set, up to changing -1 to 0 maybe, and is just the edge boundary normalized by a factor of 2 to the n-1. And it's called the total influence because it has some interpretation from social choice. So instead of talking about small edge boundary, you can talk about small total influence, and that's the same thing. Okay, and so far it looks like we talked about two unrelated problems, one about total influence and one about Fourier concentration, but it turns out that they are related. And what we're going to talk about is that something that tries to answer both of them. So basically, we want to say that small total influence implies Fourier concentration. So basically, we wanted to find criterions that imply Fourier concentration. So we have this small total influence, and wanted to understand when do we have small total influence. The answer is that you have to be Fourier concentrated. So it sort of tries to answer both of them. And so are there any questions so far?
Can we say something for the inverse problem when we know not exactly the set is a minimizer?
Yeah, if you know the set is exactly a minimizer, then you know its structure, and yeah, if you know, you also have some stability results, but not the ones that we want. So we don't have any inverse result, even if close to minimum, we interpret it as up to a factor of 1 plus epsilon. Don't know. And here there is this open problem. Which follows, I guess, from the entropy influence, Fourier-Entropy influence conjecture of Friedrich. So this is a corollary of it. So suppose so suppose that the total influence is small. Then F is so Fourier concentrated. So if F has small total influence, then it's Fourier concentrated on exponentially many Fourier coefficients in K.
F is always Boolean.
F is Boolean. Yeah. Yeah. So this is for epsilon. Okay, so we fix epsilon, and let's think of epsilon as like some small constant. Then this tells you that if the total influence is smaller than K, then there are exponentially many Fourier coefficients in K, that F is concentrated only on those Fourier coefficients. Okay, this is still open, and also something more weak, also open. a weaker one that says that if the total influence for F is at most plane, then there exists an F. Sorry, but I just don't know what I can do. Stop the squeaking. Then the natural influence is at most K, that there exists a set S such that f of S is at least exponential in K.
So for the original problem, do they actually conjecture C epsilon or do they conjecture like 1 over epsilon?
So whatever follows from the entropy-influence conjecture, the conjecture of the Fourier-Entropy-Influence conjecture. So we'll talk about it as well. And then you can think what the dependency of C epsilon and epsilon should be. So let's state it. Epsilon, many new skills during the talk, how to lift balls and how to not make talk squeaky. Okay. So the Fourier-Entropy-Influence is so elegant that it's going to fit right in here. So it says that if we sum f squared times log 1 over f squared, this is again for a Boolean function, that this is at most a constant times the total influence. And yeah, this follows from this. And originally they weren't motivated in learning, I think, but mostly about proving some results about sharp thresholds. Somehow they were interested in the other direction of lower bounding the total influence. And then if you have some symmetry of the function, then you can deduce that the Fourier coefficients, the Fourier spectrum is not concentrated, and then the entropy is large, and then the total influence is large. Somehow symmetry, somehow this relationship between Fourier concentration and total influence, it's useful in both directions. Sometimes you can show that total influence is small, and then you get Fourier concentration and then learning, and sometimes you know that there is no Fourier concentration because of some symmetry, and then you can deduce that the total influence is large, which has many applications.
So I think it is like 1 over epsilon.
Okay. Yes, so currently what we know So for the first open problem, we know it with exponential, with e to the c epsilon k log k and epsilon instead of epsilon. So that's what we know about so far, and still open to get it to be c times k.
So this is theory. This is a theory.
This is the theory. Yeah, so this is under here, instead of having e to the c epsilon k, we have this k log k. So let's talk about proofs a little bit. Do I have much time?
What?
A lot? So are there any questions so far? Okay, so you can figure out how to make it. Okay, so let's do a warm-up and just show something quite quick. But it will teach us something. So claim is that every f is n to the total influence over epsilon, Fourier concentrated.
No, what is this? I see the IF over epsilon, but
N to the IF over epsilon Fourier concentrated. Yeah. So that's yes. So somehow every result that has a dependency on n is bad, but you should always get rid of the dependence on n.
this is KKL.
No, this is just also nothing fancy. This is about the Fourier formula for the total influence. So how are we going to prove it? Going to use the following fact. So the fact is that the total influence has a nice Fourier formula. It's this sum over the size of S of f at S squared. Maybe that justifies the normalization of the edge boundary. See no dependency on n. Well, use the total influence instead of the edge boundary. So let's prove this stuff. And you can think about how to deduce this from the fact in the meantime. we're going to define these Laplacians. And these are going to be defined by f of x minus f when you flip the ith coordinate of x.
Divide by 2.
Yeah, let's divide it. So LAF takes the values -1, 0, or 1. And it's a linear operator, so if you want to understand what it does to a function, you can understand what it does to any of the characters, and you can convince yourself that LAF is the sum over all S containing I of f at s. Right? So you can show that if the character, if the set S doesn't contain I, then the character doesn't depend the ith coordinate, and then you get 0. If it does depend the ith coordinates, then you get rid of this x line. And then these characters are orthonormal, so when you look at LAF and 2 norm squared, you get in the one hand that is equal to the sum over S containing I over f at s squared. On the other hand, you have a probabilistic interpretation of this quantity. This is the probability over x that this is the probability that when you flip the ith coordinate, it changes the value of the function. So this is also equal to the 2 norm of f, the 2 norm of LAF, and this is actually denoted by the ith influence. So this is called the influence of the ith coordinate, because you can think of f as an election, and then this is the influence of the ith voter. It's probability that the ith voter determine the outcome of the election. Okay, so we have this. And if you think of it graph theoretically about the graph of the Hamming cube, this is a normalization of the number of edges in the Hamming cube in direction I. So this counts the number of pairs x and x plus ei. That one of them is in the set, one of them you get the value 1, and the other one you get the value -1. So you can convince yourself that the total influence of f is just the sum of these. And then this is the sum over I and S containing I over f at s squared. And finally you get the sum of S f at s squared. total influence basically checks how much the function is concentrated on the high degrees. Gets like it checks how much of the mass of F is on the high degrees. It's large when the mass is on the high degrees, and it's small when it's on the small degrees. So are there any questions?
So the principle that you just erased is like small total influence implies Fourier concentration on small degree, on low degree Fourier coefficients.
The open problem. So
Yeah.
So this is the warm-up that is concentrated on the low degree, but somehow the open problem is to show that it's concentrated on exponentially many k. And yeah, so but the warm-up is what you said basically. Yeah, the warm-up is saying that if the total influence is small, then the Fourier spectrum must be concentrated on the small degrees. Okay, so let's do the proof of the warm-up. So so we're going to take our F to be the set of sets, the family of sets, such that the size of S is at most the total influence of F over epsilon. And then if we sum over S not in F of F at S squared, this is smaller than 1 over so IF over epsilon times the sum of S F at S squared and over all S, and this is equal to epsilon, because this is the total influence of F. And the size of F is at most, this is at most n to the IF over epsilon. So we can always get that F is concentrated on n to the IF over epsilon many coordinates, but we want something stronger. And I guess the first
Definitely not KKL, too simple.
this is KKL for baby.
So now you're like 1 hour in.
I should finish in 2 minutes.
With the lecture today?
Yeah, I don't know. So when should I?
Should be around an hour, but you still have it 10 minutes.
10 minutes, okay.
We start.
Yeah, I can stop whenever. Like, what should I?
10 past.
10 past. Okay, so. And then, okay, so like I said, you shouldn't prove results that depend on M, and or if you prove results that depend on and prove them as consequences of results that do not depend on it. Okay, and Friedgut gave the first bound that does not depend on N, and it uses some ideas from KKL, of Cantelli linear, and what it proves is that every F is e to the c ix squared over epsilon squared epsilon.
Does this actually appear in his paper? Does this actually appear in his paper, or is it?
It follows.
follows?
He cared about something else. Okay.
Will you prove this?
Yeah, this will prove. And the idea is a bit counterintuitive. So earlier we wanted to show Fourier concentration. We said that all the mass of a function with a small total influence is concentrated on the low degrees. And to prove Friedgut, we are going to use the opposite. Something that says that most of the mass of a function is concentrated on the high degrees. And, so the idea is to use Fourier anti-concentration. Somehow, anti-concentration results. To reduce Fourier concentration. It's like judo, you use the power of your enemies in your favor. And yes, I'll state what the result that KKL proved. So that's the Cantelli-Linear theorem. And suppose that you have a function f. Now it will be convenient to let it be from -1n to 0, 1. And what we're going to assume is that the expectation is small. I'm going to stick with this one. Okay. So with expectation, okay, let's just denote the expectation by epsilon. So now we're going to take the sum over all the sets that are small. Of f at s squared. So earlier, when we wanted to prove we proved Fourier concentration, we showed that almost everything is inside the set. Now we're going to show that almost nothing is inside the set. this is at most 3 to the d times epsilon to 1.5. So we should think of d as smaller compared to log 1 over epsilon. And then, yeah, I guess one way to think about it is to compare with the trivial bound. So we always can take the sum of the small Fourier coefficients and say that this is at most the 2 norm of f squared. And this is epsilon.
Excuse me, what is the power of epsilon?
And 1.5. And so the trivial bound would be epsilon, but you get something much better. You get epsilon to 1.5. Somehow, if you have a function, if you have an indicator of a small set, then most of its Fourier mass is on the high degrees. Okay, so we're going to prove Friedgut by using this theorem. And this theorem we're going to prove using the following lemma, which is called Bonomi's lemma. And says that if, let's just give a definition, so the degree of f is, so its degree is a polynomial, so it's the maximum over non-zero Fourier coefficients of the type of f. And what Bonami proved is that that you can upper bound the 4 norm of a low degree function in terms of its 2 norm. So the 4 norm of f is at most 3 to the d over 2 times the 2 norm of f. And somehow we can think about it as so you have a large gap between the 4 norm and the 2 norm if the function behaves in a crazy way, if there's bad tail bounds, there would be a gap between the 4 norm and the 2 norm. And what this theorem tells us is that low degree functions, they behave reasonably. There is the 4 norm is not too far apart than the 2 norm.
And this is for functions.
This is now no.
Yeah, there's
now
no
f is not
definition.
Boolean. Yeah. Very much. F should define, by the way, L4 norm. Someone wants me to define.
Just try the definition, will take you a moment.
Okay.
But it's also being recorded, so for posterity.
Okay. Fine, so the LP norm of F is the expectation probably I should say that in a probability space, if you look at the, let's say, L2 unit ball, the L4 unit ball is smaller. Yeah, so somehow in probability spaces, the L2 norm is always smaller than the L4 norm. And then you have, for low degree functions, somehow the gap between the L4 norm and the L2 norm is not that substantial. Probably I should also give this example. So let's say that I have a random variable x that takes value say 1 over root t with probability t. And 0 otherwise. With a very small probability, you get this large value 1 over root t, and otherwise you get 0. Then here the L4 norm is much larger than the L2 norm. So the x4 is so the L2 norm is 1, but the L4 norm is going to be so p to the 1 over 4, the minus 1 over 4. So if p is small, this is very large. So somehow, yeah, and if you look at the distribution of a Boolean function that takes one with a very small probability, its distribution behaves like this, right? It takes one with a very small probability. So if you normalize it, it behaves in this fashion. And what Minzer lemma tells us is that low degree functions have the opposite behavior. So this is the behavior of low degree functions. Here, this is the behavior of Boolean functions. With a small expectation. Okay. And here Boolean is 0, 1 valued. To have this difference in behavior that you can leverage into showing that Boolean functions with small expectations are not correlated with the low degree functions. And this means that all the mass is on the high degree. Okay, so yeah, now we'll continue after.
So, yeah. Okay.